Thank you so much. It's great to be here. I was just telling Daniela that I think I've never given a seminar with this high a ratio of co-authors of mine to non-co-authors. And I'm not making a comment about the denominator, really just the numerator is really high. And not just co-authors in general, but actually the work I'm going to present today is joint work with many people in this room, actually. Here they are. This is so Amir, and these are all people you know, I'm sure. Amir and Keshav are first year PhD students at UW, and I forget Biostat, I think. Okay. Anna is a fifth year PhD student in statistics, and Lucy is a sort of recent grad who I worked a lot with when she was a PhD student here. And Daniela, I've worked with for many, many years. So this has a lot of UW in it, or maybe a lot of Witten in it. I'm not sure what the interpretation of the W is that I see all over the place here. But okay, so I was at Cornell for 5 years before coming to USC. And when I was at Cornell, a neat thing was I got to do a lot of statistical consulting as part of my job. And if they're like looking back, and the neat thing about Cornell is there's this School of Agriculture, and there are all these departments that you wouldn't think are departments, but they are. And so just the variety of research topics that people, somebody studying wine, for example, came with statistics questions once. So tons of these topics. And looking back, if there's one statistical idea that I would say the most to people, it would be sample splitting. Because we all know, as this AT mineral processing company says, sample splitter is the basis for good analysis. And so apparently that's true in mineral processing, but it's definitely true in statistics. And so today's talk is actually about sample splitting, or rather an alternative to sample splitting. And I think it's a little funny to be giving a talk about an alternative to sample splitting, given just how useful sample splitting is. But so let's start by sort of remembering why sample splitting is why we like it so much as statisticians. So the general idea is if you have a data set, for example, so on the left here, like an N by P matrix, where we're thinking of every row as an independent, identically distributed draw from some distribution. The great thing is we can split it into two sets, X1 and X2. And why is this useful? Well, we can think of a lot of situations, but two general scenarios. So the first is sort of more machine learning, predictive settings, where we would use part of the data, X1, to train some maybe potentially complicated model. And then if we want to know how well it works, of course, we shouldn't use the data we trained on. Instead, we would have this X2, this fresh part of our data, and use that to estimate the prediction performance. So that's one reason we like this approach. Another scenario, which is maybe more, comes up more in more scientific applications, is to avoid data snooping, right? So we use part of the data as in an exploratory phase where we generate hypotheses, and then when we decide on a hypothesis we care about, we now want to see if that's, validate whether that's actually whether the data supports that hypothesis or not. And in order to do that, we know we shouldn't use the same data. And so that's where we having this X2 is a very useful thing for validating hypothesis. So why does this work? Well, at a high level, it works because we have two data sets that are independent of each other, and yet they come from the same underlying distribution. And that's all great. So why would one come up with an alternative to sample splitting, given how good it is? So we have here sort of some potential downsides. And I guess what I would say at a high level is sample splitting is just such a nice, simple idea that people use it everywhere. And in fact, they even use it maybe sometimes in situations where maybe it wouldn't be the best thing to do. And that's sort of the situation that we're thinking about in this work. So where might it not work well? Well, for one thing, we were assuming that the rows of our matrix were independent, but we know that that's not always the case. For example, data that's collected over time sometimes has dependence in the rows, so that wouldn't have the x1 and x2 independent. And the other downsides here, I actually have separate slides for, so let me just go forward. So for example, outliers, right? It's a little awkward. So here we see maybe like a regression setting where we have a really nice relationship, but we have an outlier. And the thing about sample splitting is, at the end of the day, that outlier is going to end up in either the train or test set. And dependingly, you'll get, whether you train on the one with the outlier or not, you're going to get very different results, which seems a little unsatisfying. Another thing is sometimes our questions, we're really interested in each observation on its own. So for example, in the pandemic, there were so many interesting questions that people wondered, and so data collected across every state in the US, and we really wanted to know something about each and every state and maybe perform, end up, train something across the entire country. And then we really care about making a valid statement about every state. And it's not so nice that if we trained on just 30 states and then tested on the remaining 20, well, if you lived in California and California was in the training set, then you don't get to find out what's validated about California because it was used in that training stage. So the situation, more generally, where you're observing observations, like in this case, like the 50 states, and you think that each observation has its own parameter, and you want to make some inferential statement about that parameter, this idea of sample splitting doesn't really help you there. And to specialize even more, we could imagine like normal data, the normal means problem, where we are curious about the mean of this normal. And an even more special case of that would be fixed X regression. And so in fixed X regression, if you excuse the switch of notation where I'm going to go to regression notation, where now my random variable is no longer X, I'll call it Y. But the point is, in some situations, our X's are truly fixed. Like we were running some designed experiment where we set a device at a particular set of levels X. It's definitely not that it was drawn randomly from some underlying distribution. And yet sample splitting is like such, this idea of cross-validation is just such a natural tool that we always want to use that we tend to apply it even in these situations where we know that the X matrix is itself fixed, not random, right? And yet we pretend, we'll say, oh, well, think of yi comma xi as these IID pairs from a distribution, but that's just not that doesn't really match reality in every situation. Okay, so finally, one more situation that we think about, so at a high level, there are different unsupervised learning problems where it seems to have this same aspect where sample splitting doesn't seem to work. And so change point detection is an interesting case of that. And so in change point detection, right, we might want to like just, eyeballing this data, maybe we see three different values of the mean. And so how would we do sample splitting? Well, maybe the first thing you'd think of, which is actually something that is done a fair bit, might be to just alternately, every odd point, put that in training, every even point, put it in the test set. But that's sort of an arbitrary choice. And you might, usually in sample splitting, we might like to repeat over many random splits, train and test splits to reduce the randomness that comes with that splitting process. But here, in this example, I forget, maybe I have 30 points here or something. How do I get, if I want to repeat this 100 times across 100 random splits, what does that even look like? It stops sort of being clear how exactly you'd go about doing that. Okay, so so all of this suggests that maybe one wants to think of options beyond sample splitting. And so there's been some interesting work, and I'm going to build up to work in a few minutes that comes out of this audience in particular. That was the starting point for the work I'm going to talk about today. First of all, I wanted to talk about this thing called a UV decomposition, which was introduced by these authors, Racines and Young. And basically, they set out an interesting goal, which they pursued specifically in one very specific example. But the goal is an interesting one and relevant to us. They basically say if you start with a random variable, and by the way, when I talk about a random variable in this talk, sometimes I'll be talking about like literally a scalar that's random, like a single number. Sometimes I'll be picturing a full matrix, a random matrix. And pretty much everything I'm going to say doesn't really matter what it is. But anyway, so they're saying, imagine you start with some random x, and they say, can we think about somehow splitting this into a u and a v that are both random, that depend on x, but they also depend on some random w. So it's as if you're just infusing some noise into the data. And they say, wouldn't it be nice if you could do that in such a way that u and v are actually independent of each other? And yet u and v together contain all the information that the original x does. Okay, so the work we're going to talk about today, we're basically going to accomplish this goal in a wide range of settings. But I'm going to start by saying in this paper where they proposed this, what did they do? So they focused on a multivariate normal in which the mean is unknown, but the variance, the covariance matrix is known. And they used this strategy that that appeared earlier in this paper by Tian and Taylor. I understand Jonathan Taylor was here recently, I guess in the stats department just last week, I think. So what do they do? If you start with x, they do something very simple actually, which is you can generate a w to be a multivariate normal vector that is mean zero and covariance identity. So it's really just like standard normal noise. And they add that vector to to x to form u, and they subtract that same vector from x to get v. And the wonderful thing about multivariate normal is we know that we could just think about covariances, and that tells us about the dependence. And it's easy to verify, though still, I think, a little surprising that u and v, even though they both have x in them, are actually independent random variables. And not only that, but we also see that u and v contain all the information x had, because we can always get back to x just by adding them together. Okay, so this paper led then to another paper called data fission. And data fission was thinking about generalizing the goal in Racines in a sort of a different way. But they did dwell a little bit on things like what we'll be talking about today. And in particular, they added, so not only could they do the normal case that was there already, but they also said you can do it for Poisson data. And we'll talk more in a minute about that. Okay, so now comes this paper that came out in January called Data Thinning for Convolution Closed Distributions. And this is, Anna, Amir, Lucy, Daniela, all here. And when I read this paper, I got very excited, and I hope to convey why. So what are they doing? Well, basically, so they said let's consider convolution closed distributions, or rather families that are convolution closed. So what does this mean? This means families in which if you take two random variables that are in that family, and if you add them together, if those were two independent random variables from that family, if you add them together, you get a random variable that's still in that family. So we know that holds for normal. If you add two independent normals together, you still have a normal. if you add two Poissons that are independent together, we still have a Poisson. So those are examples of convolution closed families. And so what did they say? Well, they came up with a way to generate, if you start with an X that's from one of these families, they can tell you how to generate two random variables, X1 and X2, with the following three properties. The first thing is that X1 and X2 are independent of each other. Second of all, if you add X1 and X2 together, you get back to the original X. And then lastly, and this is kind of a nice thing, though we'll see later, sort of non-essential, X1 and X2, their distributions actually are in the same family that X was in. Okay, so in a picture, what does this have to do with sample splitting? Well, in a picture, remember, sample splitting was a way of getting an X1 and X2 that were independent of each other, and yet somehow their distribution was like the original X's distribution. So convolution closed data thinning is a similar picture, but a little different, which is, again, we've broken X, we've split it in a certain way into an X1 and X2 that are independent of each other, and yet they can be recombined to get the original data. And in this case, they say, well, if you add X1 and X2 together, you can get the original X. So to look at the outlier example that I mentioned before, where with sample splitting, we'd have to put the outlier either in the train or in the test set, and it's a little awkward. What would this sort of splitting that Racine's and actually, so all three of these papers considered the normal case, what would that do? Well, it would actually do something like the following, where both your training and your test, these two split data sets, both have an outlier in them. Okay, and so we see that somehow this would be a lot stabler than that case where you put the outlier completely in just the training set or completely in the test set. Okay, so the great thing about this convolution closed property is there are a lot of families beyond just normal and Poisson that are convolution closed. And so they're able to really add to the set of distributions where this sort of splitting is possible. So they can do negative binomial, gamma, binomial, multinomial, all these things. And furthermore, rather than just, so far I've been talking about splitting into just two pieces, X1 and X2, but sometimes it's convenient to have, a training, validation, and test set, or, or you have K-fold cross validation. So they can actually split into K independent parts in all of these cases. And by the way, everything I say in this talk, I'm only going to talk about splitting into two from now on, but everything we do in our paper actually can be done into K parts. Okay, so just to give an example that might be a little more exotic looking. So for example, their framework works here. If you start with a gamma random variable, and a gamma has two parameters. And so we'll imagine that the first parameter is known, and we'll consider the family of distributions indexed by theta. So theta will be the unknown. And what they show is, amazingly, if you generate z, which is a beta random variable, and notice the parameters of this beta doesn't have a theta in it. So the thing that's, so this is something you can do even not knowing theta. So you can generate a beta random variable. And if you do that, they say, take that z that you just generated, the beta, and multiply it by your original x, and call that x1. And then to get x2, just do x times 1 minus that z. And amazingly, it turns out that x1 and x2 are independent of each other, and they're themselves gamma random variables. And not so amazingly, because we can see it sort of obviously, if you add them together, you get back the original x. Okay. So the goal for today's talk, there are a few of them. I have no idea why I have an apostrophe between the L and S, I'm sorry. So the first thing is, like, when I read this paper, I was really excited because it just seemed so magical that you can have two independent things and yet they add together to a random variable that you measured to your data. And so, one goal is just like trying to understand convolution closed thinning. What is behind it? Like, why does it work? And there's some question about like which parameters do you need to know or not, and trying to clarify that. And then maybe the biggest thing is trying to understand, well, what happens if you're not in a convolution closed family? Can you apply this to, for example, a beta distribution, right? A beta we know is supported, it describes random things that are on the unit interval. So clearly that can't be convolution closed, because you could definitely add two betas together and get something that, you know, is bigger than one. So what about all those other distributions? Can a similar idea work here? And so the generalized data thinning that's in the title of this talk refers to the work I'm going to talk about, and that's basically going to allow us to generalize to far more distributions than just convolution closed distributions. And in so doing, we'll actually have a better understanding of what's happened in convolution closed thinning. And a really nice thing is actually it's going to show that even sample splitting is an example of this generalization. So generalized data thinning actually includes sample splitting as a special case. Okay, so I'm going to tell you about generalized data thinning, unless anybody has any questions or comments. Yes.
So we split the things like A first, you know, all of those together. Sufficient for the parameters of this, or like those sufficiency interactions.
Oh, so I haven't mentioned sufficiency yet.
Oh, okay.
But we will get there soon. Yeah. Yeah, great. That's kind of the punchline. You just gave the punchline. Okay, so I'll keep going then. So this is what I said about convolution closed thinning. It had these, you're aiming for an x1, x2 with those three properties. And so now I'm going to say what we're going to modify to get to this generalization. So first of all, the title will change. It's generalized data thinning. Good. We don't want to assume that x comes from a convolution closed distribution anymore. We'd like to consider other kinds of distributions. What else? Well, if you think about it, why is it useful that x is equal to x1 plus x2? Well, it's useful because that's kind of evidence. That's our way of, or that's their way, I guess, of demonstrating that you haven't lost information, right? Because there are plenty of ways to add noise to your data to get independent things, but most of those sort of naive ways of doing it would actually destroy the information that we had in our data, and we wouldn't want to do that. Right, like sample splitting, we know when we split our data in half, we could always put it back together and get the original data set. So we haven't lost any information in that splitting. So when we say x is equal to x1 plus x2, that's kind of a way of saying, look, yeah, you have these two independent x1s and x2, but in total, we still have the information, if you put them together, that was in the original data set before splitting. Okay, so a key thing that we're going to do in this generalization is we're going to say that it didn't really have to be addition. All we need is that there's some deterministic function t that you can take that x1 and x2 and put it back together and you get back to the original x. Okay, and then this last property, I've already sort of said this, but there's really no need for x1 and x2 to belong to the same family. That was a really nice kind of convenient thing, but strictly speaking, if we want to generalize to other distributions, we don't really need that one, because at the heart, the two things we care about is that x1 and x2 are independent, and second of all, that we haven't destroyed information about the unknown parameter theta in doing the splitting process. Okay, so there we go. Not the prettiest view, but you can see how it compares to convolution closed. And in a picture, if this is what convolution closed data thinning was doing, this is what generalized data thinning is doing. So I just replaced the plus sign with some function t. And more pictures. So what are we going to do? So in generalized data thinning, we're going to say that we need some way to where you start with x, and we're going to come up with this thing which we'll call g sub x, which is you can think of it as a mechanism where you put in x, and it describes a distribution that is going to produce x1 and x2. So like in sample splitting, that's the thing that takes x and randomly puts half of the rows in x1 and the other half of the rows in x2. Okay, so it's this thing that's going to inject randomness, but it does it in a very particular way because, first of all, this needs to be something that we can do in practice. So G sub x, this distribution that we're sampling from to get x1 and x2 cannot depend on unknown parameters. And second of all, these x1 and x2, as I've said before, they need to be such that there's some deterministic function t that can put it back into the original x. And the reason that's important is it means that's our way of having evidence that in doing this splitting to x1 and x2, we haven't actually, so we've introduced noise and yet we haven't actually lost any information about our data x. Okay, so we can go to an example, sort of, this is a textbook example of thinning. And in fact, like I remember, I think as a master's student taking like, I think a stochastic processes class where it was sort of a probability exercise, but seeing this idea of thinning a Poisson process. And, but we can do it with just a Poisson random variable. And so here, x would be Poisson theta. And what do we do? Well, the trick is you can generate x1 given x as a binomial, where that binomial has x trials and some probability. We might as well take it to be a half. Okay, so basically the idea is to form x1. So if you think about x, you have x different things and you flip a coin for each of those, x1s, and every time it's heads, you put it into x1. Every time it's tails, you put it into x2, right? Because by the way, so x2 is just x minus x1. All right, and you can show that these are independent of each other, but it's actually clear from this bottom, the definition of x2, that adding x1 and x2 together would give you back the original x. So, and probably what the homework exercise I recall was to show what would the distribution of x1 and x2 be. And the interesting thing is they are themselves Poisson random variables, except the rate parameter has gone from theta to half theta. Okay, and we also know, so if we take t to be summation, we know that if you add two independent Poissons, the rate parameters add together. And so we see that we would get a random variable that has the same distribution as we started with, which has to be true because we know we get back the actual x that in the first place had that distribution. Okay, so now to jump from a textbook thing to a new result. So this is applying generalized data thinning, which we'll call GDT, to a beta family. And remember, I said beta is not convolution closed. So this is something that will specifically, it'll have to use a t that is not addition anymore. And so what do we do? And by the way, so this family, just the notation that we use throughout is that theta is the unknown parameter. And if there's any other parameter, like here, there's the Greek letter beta there, we assume that that one is known. And so in this case, what do we do? Well, so x would be beta theta beta. So if we assume that, we're going to be able to produce a sampling mechanism, GX, that uses knowledge of x, but it doesn't use knowledge of theta. It's allowed to depend on beta, though, because we're assuming beta is known. And if we do that, it turns out that the first distribution will be beta 1/2 theta 1/2 beta. And the other distribution, x2, will be beta 1/2 theta plus 1/2 plus 1/2 beta. Okay, so let me just briefly interrupt to say that this result, if you see how it's proved, it's like amazing, and this is crazy. But Amir, first year, did some crazy calculations to come up with this really remarkable result, which I should just so you can appreciate it. So the function t, it turns out, is the square root of the product. So it's like the geometric mean of x1 and x2. So it turns out that the geometric mean of these two beta distributions gives you a random variable that's beta with a slightly different theta. Okay, so one thing that's interesting about this example is it shows that x1 and x2 can actually have different distributions from each other as well. But this is useful. Why is this useful? Because as long as we know what the distribution of x1 is, we can, for example, choose to estimate the theta. And then as long as we know what the distribution of x2 is, we can validate that estimated theta using this data. Okay. So I've shown in a schematic what generalized data thinning is. So what remains would be to say a little bit about like how we actually define this thing. So we start with x being, belonging to some distribution p theta, and p theta is, belongs to some family of distributions that is indexed by theta. And so we're going to say, what does it mean to thin that family using a particular function t? So we'll say p is thinned by the function t. What do we mean by that? Let me go here where this is the same definition, just shifted upward, because I can do it now with this picture. What it means is we're going to come up with this sampling mechanism, this gx thing, which, so conditional on the observed data x, we're going to be able to generate two new random variables, x1 and x2, using this gx. And in particular, it means that we can find a distribution gt that does not depend on theta. Okay, so in other words, it's something that we can actually in practice use because it doesn't depend on unknowns. And so once we know what this function gt is, we can plug in the observed random variable x into there. And that gives us the sampling we want. And then the second part of this is there's an accompanying deterministic function t that will give us from x1 and x2 back to the x we started with. Okay, so that's what we mean when we say a family can be thinned by a function t. All right, so let's return to this normal location family example that we started. Remember, Racines and Young did it, Lehner with the data fission, and then the convolution closed paper. Also, all these looked at the normal case. So now we can look at the normal case again. And so in our generalized data thinning framework, what we would say is the function t that you're thinning by is addition. And furthermore, the sampling function gt that you would use would be the following, which is, if you look at it, it kind of looks a little complicated. What we see is this covariance matrix. This is a degenerate multivariate normal distribution. Like the covariance matrix is not full rank. But the crucial thing is that there's no theta in it. And sampling from this actually can be accomplished doing the following, which is sampling. You'll recognize this, right? This is exactly the original Racines idea, or actually even going back to Tian and Taylor, which is having a random vector w and adding it to x and subtracting it from x. And so here we have an additional scaling, but at a high level, this is exactly the same thing. Okay, so that is in our GDT framework as well. Okay, so there's so many questions now, right? So one question is, how do we go about finding families that meet? Because I've just said a definition, which doesn't mean that this is something we can necessarily do. Of course, we saw in the beta example that somehow, we were able to do it. So how do we go about finding families that can be thinned? That's the question. And like, is there any unifying principle for how we go about choosing that function t? Like, how do we know if a given function t will work or not? And then a practical issue, which is, where do you get this sampling function gt from? Okay, so we're going to try to answer all of that with the main result of our paper, which tells us how to do it. And as Ethan alluded to, the key principle, it turns out, is the function t needs to be a sufficient statistic. But let me elaborate a little more. So remember, we start with x belonging to some, or coming from some distribution p theta. And so what the theorem says is, suppose you had figured out, you found a T that works for this distribution, P theta. So in other words, you have a way to generate X1 and X2 that are independent of each other. And yet if you apply T to it, it gets you back to the original X. Okay, so suppose you had achieved that. This theorem tells you that actually that function T would specifically have to be a sufficient statistic. It has to be a sufficient statistic. For what? Well, it's a sufficient statistic for theta based on X1 and X2 together. Okay, so a reminder, what is a sufficient statistic? Well, at a high level, it refers to this idea of data reduction. And sometimes you have a summary of a data set that has lost a lot of information about what you care about. But a sufficient statistic is a way of reducing a data set down to some summaries in such a way that you have not lost any information about the parameter you're hoping to estimate. And the way of saying that is saying, the data set conditional on that summary that you've kept, the remaining randomness in the data set after you've conditioned on the sufficient statistic, that randomness does not depend on the unknown parameter at all. Okay, so the first part of the theorem tells us, look no further than sufficient statistics because it has to be a sufficient statistic, that T. And then the second part tells us how to find this function GT. It says that we should take GT to be the following conditional distribution, which is the joint distribution of X1 and X2. Remember, X1 and X2 are marginally independent. And they have whatever, assuming that how to thin, they have whatever distributions they have. And so now once we know the joint distribution of X1 and X2, it's perfectly valid to ask the question of, okay, for this particular function T, what is this conditional distribution of X1 and X2 conditional on T? And I was just mentioning the definition of sufficient statistic, and basically being a sufficient, T being a sufficient statistic for theta is identical to this property, this distribution not depending on theta. This conditional distribution cannot depend on theta because T is a sufficient statistic. Okay, so this has told us, this is actually a very practical thing because now this tells us how we can go about finding examples where generalized data thinning occurs. And so we have sort of a recipe. And our recipe is the following. We choose any two distributions we want, call it Q theta 1 and Q theta 2. And these will be the distributions of the X1 and X2 that we get out, okay? Next step, we look at we think about this pair, X1 and X2, which has a likelihood that we know because it's, right, these are independent random variables having marginals Q theta 1 and Q theta 2, which again, we get to choose what they are. And so then we find a sufficient statistic for theta based on X1 and X2 and call that T. Okay. So now let P theta be the distribution of T of X1, X2. Okay, and by our theorem, that means that family can be thinned. And I know that we'll go to an example. Sorry that this is a lot for a talk, but sort of one-line summary of what this says is it tells us what sorts of families we're able to thin. And in particular, we can thin the distributions of sufficient statistics. So if you can find, you start with a Q theta 1, a Q theta 2, and you find a sufficient statistic based on that, we can thin that statistics distribution. All right, so basically what we do in a lot of our paper is we start with two Qs. We just say, oh, what about this as Q, this is Q, and then we see what T comes out and we see, does that T have a name of a distribution that we like? Great, now we know how to thin that distribution. Okay, so I want to give some examples and let me see how I'm doing with time. This goes another 15 minutes or so, or 20, I don't know. Okay, so we can give different examples, but since sufficiency is sort of the key property here, it's kind of useful to organize our examples based on different types of sufficient statistics. And there's this really interesting result, and I think was it, I forget, Anna, I think maybe pointed us to it. Sorry if it was somebody else. But basically in the 30s, these 3 papers categorized sufficient statistics into just basically 3 categories. That definitely we know exponential families have sufficient statistics prominently there, because when we write out the form of the likelihood, we say, oh, in the exponent there, we have that T of X, that's the sufficient statistic. So that's one kind of sufficient statistic. Another are families where the support of the distribution is controlled by a parameter. Okay, and having taught theory of stat for over and over again to undergrads, my favorite example was this uniform 0 to theta, right? And it's Orca's favorite too, apparently. Right, so right, okay, so we have, right, so uniform 0 theta is an example of that. And so there, for example, in this case, the sufficient statistic is the maximum of, if you've had n IID draws from a uniform 0 theta, the maximum would be the sufficient statistic for theta. And then the last category are sufficient statistics whose dimension grow with sample size. And there we might think about a non-parametric setting where we have like an IID sample of size n, all drawn from some distribution f. And there we would have like the order statistics would be a sufficient statistic. So that's an example where the dimension is growing. So basically we can find examples where we can do GDT in all 3 of these categories. And I'm kind of thinking I'm going to sort of skip. I've already given you an example of exponential families, and we can do it sort of generally, but I think for a talk, it's probably not so interesting. So I'm going to, but I will say that in the special case of a natural exponential family, this allows us to see what's happening in convolution closed thinning in a very nice way. And basically the reason addition comes up there is because in a natural exponential family, the sufficient statistic is addition. Okay, so we can recover all of these examples of thinning using addition, and these were all the examples that appeared in Anna and well, many of my co-authors' paper that appeared in January. So, so we can recover that in a special case. So that's great. Exponential families are done. What about the uniform? So the uniform is kind of interesting, I think. So we can apply our recipe. Remember, the recipe says choose any 2 Q distribution, a distribution for x1 and a distribution for x2, and then see where that leads you. And so, of course, I'm doing here the thing that one does after doing research, where you make it, seems like a brilliant guess, but in fact, there was a lot of banging heads against tables to get to decide that this was the right starting place. But the interesting thing is if you start with this as your Q1 and Q2, so by the way, what am I saying? So sorry, let me just slow down here. So what is the distribution of X1 here? Well, it's a beta distribution with parameters 0.5 and 1, but they're scaled by a parameter theta. Okay, so this is a scale family. Because remember, a beta distribution goes from 0 to 1 as its support. And so we're just imagining stretching out a beta distribution, but we don't know how much we're stretching it out. And what does a beta 1/2 1 look like? Well, it's basically something that is bigger towards 0 than 1. So it's kind of dropping. And so we're saying if you start with x1 and x2, both of that form and independent of each other, that's what that product is. It's saying they're independent. What is the sufficient statistic? It turns out you can convince yourself that it is the maximum of x1 and x2. That's sufficient for theta under that model. And so the theorem, or following our recipe, since we're following our recipe, that tells us that we'll be able to thin whatever the distribution of the max of x1 and x2 ends up being. That's the distribution we'll know how to thin. And I guess the title gives it away, but what is that distribution? It turns out the maximum of those 2 things is a uniform 0 theta. So having applied our recipe, that means that we have established that if you want to thin a uniform 0 theta, you can do so using the maximum as that function. So I think I have this as a picture. So if we have a uniform 0 theta, we can thin it into 2 scaled beta distributions. And if you want to, proof that you haven't lost any information, you can use that function t being the maximum of the 2. Okay, and the maximum of these 2, so we have x1 and x2 that are independent of each other, but the maximum of the 2 of them gives us the original x. And remember I said that x1 and x2, they're being, the beta parameters are such that these are kind of bigger towards 0 than they were towards 1 or towards theta. And if you think about it, taking the max of 2 things is going to tend to make this stochastically larger. And it turns out that we've chosen all these parameters such that when you take the maximum of these 2 things, instead of being sloping downward, it ends up being flat, like a uniform. Okay, so what is this function gx that will take us from a uniform to these 2 separate scaled betas? Well, I'll discuss that next. In fact, maybe I think I'll skip that. I'm happy to answer more about that if people want to see how we do that. But we can verify that this really does work, which is neat, that if you start with these uniforms, we did simulations where you find that actually you get out scaled betas following the sampling mechanism that we worked out. Okay, so that takes care of the first 2 cases, and that leaves situations like this non-parametric setting where things grow with sample size. And so for this, there's one other part to the story, which makes the picture uglier, but I promise it's like pretty simple. The idea is sometimes you start with X, but rather than doing generalized data thinning on X directly, it's convenient to instead thin S of X, where S is a sufficient statistic for theta. Okay, so this is the second appearance. We have 2 sufficient statistics now in this story, right? We had T being a sufficient statistic when you were using data X1 and X2 together. Now we have S, which is another sufficient statistic. And the point is, going from X to S of X, you lose no information about theta because that's what it means that S of X is sufficient for theta. Okay, so going from X to S of X, we're fine. Then we do the generalized data thinning process, which can get us 2 independent random variables that can be recombined to get back to S of X. All right, so the main thing is that no information is lost about theta. And we have a written whatever, that's true. So, so to this example, we have, imagine you have X being X1 to Xn, IID samples from some distribution F, which belongs to some non-parametric family of distributions. So can we do generalized data thinning in this case? And the answer, which again, I'm going to kind of skip over, but the answer is yes. And the idea is we'll do this indirect thinning idea where we'll sort the X's and then we'll thin that. And the way we thin that is, yeah, sorry, I'm not going to actually dwell on this, actually explain it. But the point, the exciting conclusion out of all of this is that actually applying the GDT process recovers exactly what sample splitting is in this case. So this framework is broad enough to include sample splitting, which shows that actually like all these data thinning things are really all examples of the same thing, which is just using sufficient statistics in a very particular way. Okay, so those are 3 examples, but actually we have a very big table in our paper of families where we know how to do generalized data thinning. Okay, so all right. One question is, can every family be thinned? And interestingly, we have a result saying that no, not every family can be thinned. And our example is the Bernoulli family. And I'm going to skip over this, even though it's pretty interesting. So because I wanted to end with an application. And in particular, this application is about wind speed data. And there's this R package and associated paper by Killick and Eckley in 2014 that models the daily differences in wind speed. And they model it as xi as being normal with mean 0, and then a variance that might be changing according to what day you are. And they're thinking of it as sort of piecewise constant. So that's why the change point model. And here I have a plot which is from their paper where they've run a change point algorithm on this data. And well, I mean, I'm sure you see where this is going. We would want to know, like, do we believe these estimated change points? We want some way to actually validate whether these are real change points, because we know at some level, like if you just ask an algorithm to find a place where there appears to be a difference, it could do that. And so how would we go about doing this? Well, if you come to me and without looking at the data, say, I think there might be a change point on December 31st, I would look at the data just to the left of December 31st and the data just to the right, and I would do some sort of 2-sample test to ask if they're different. Okay, but we realize there's a problem with that, which is if we now have a change point that wasn't just December 31st without having looked at the data, but instead it's the day where this change point algorithm thought there might be a difference, well, then we have a selection problem. And just to convey that this selection problem is a bad one, we have a simulated data set where there are actually no change points. And yet we run the algorithm and we get 42 change points. And when we do this sort of 2-sample test in neighborhoods around these change points, we actually find 20 rejections. And yet this is null data, so we know that those are all false positives. And so what can we do? Well, we can try a generalized data thinning. And so we do that. I'm going to skip the details of how we do it, but the point is we can do it. And so now we have 2 split data sets. And so in red, I'm repeating what we had before, but in blue, I'm showing the result of applying the change point algorithm to the first of these 2 thinned data sets. And so that's what the blue lines are. And then we have a blue star wherever we would get a significant finding, like found in doing the validation that it's actually significant. And what you can see is there are no blue stars. In other words, we didn't reject at all. And so that seems promising that this is guarding against this false positive problem that the naive method had. And so we might, ask about power here. And so we could say, well, what if we simulate a situation where there actually is a change point? And remember, the change point here is a change in variance, not a change in mean. And so the naive, again, it sort of gets the right change points, but it also has a ton of wrong change points. And in the lower panel, this is what happens if we do the explore and validate separate approach. And what we find is that there are 3 on this run. There were 3 rejected change points, and if you look at it, that's like exactly where the variance actually does change. So that's promising. But there is a problem, something of a problem, which is So now we can apply it to the actual data. So here on the wind speed data, we apply it, and the great thing is instead of having 26 rejections, which seems way too high, there are only 3 places where there seems to be statistical evidence of actual change points. Okay, but there is something a little that you might be wondering, which is, the splitting. It's a random splitting into train and test. And you could say, well, couldn't it turn out differently? Like if I had a different random split. And as I mentioned at the beginning of the talk, like with sample splitting, we usually like to do this over many train test splits, right? That's something that you see a fair bit in different papers. And yet in the change point setting, if we were doing sample splitting, it wouldn't be clear how you could repeat this 100 times. And so, but the nice thing is with generalized data thinning, we can very naturally repeatedly get these, split our data set in many ways into X1 and X2. And on each X1, we estimate some change points. On each X2, we validate whether we believe in them. And so doing this, we get the following. Let's just look at this bottom plot. This is showing across 100 repeats of this thinning process. It shows, it counts how many times a particular location was selected as a validated change point. So not only was the change point, discovered in the first half, but furthermore, it came out significant in the second half. And so we see some peaks here, and large values, and they're not huge peaks, right? Like this is maybe happened about 20 times out of maybe 20% of the time. So maybe there's some evidence, but maybe not very strong evidence. But at least it shows how it's useful to have done this thinning operation, because it allows us to repeat it many times. Okay, so thank you. That we are basically, I think, a little over time, so I should stop there, I guess. But so I'd welcome any questions or comments or criticisms from co-authors on any of that. So there.
Any questions? Yeah, so on that, you said something incorrect, so correct, but it wasn't correct. So on that uniform zero data example, the G of X randomization process should not depend on the data, right?
Right.
But the X1 and the X2 have like a data attached in front of it, so in some sense it does it. So how does like?
Yeah. So the thing that we care about is we need this function GX. Let me go back to the uniform even example. So the thing that it's just a practical thing, which is we can't allow GX to depend on theta, because if it is, that means that's not something you can do in practice. Yeah. So that's what we care about. And yet, when we put in our X here, that's going to lead to an X1 and X2 that depend on the original X. And since X had theta in its distribution, X1 and X2 will also have theta in its distribution. And we want that because that means that, first of all, it's unavoidable because we know that X1 and X2 have all the information that X did about theta. But also we want that because we want X1 and X2 to be informative about theta. And so the really tricky thing, though, is how can you preserve the information about theta while having these two parts be independent of each other and yet not need to know theta in order to do this thing. So it's like a very particular way of injecting randomness into X. Yeah.
I have a question about the power compared to sample splitting. Like in the case where you can do both, like is the same thing, but like in the case where you have IRB data, you can do both sample splitting and the data thing, and you validate the same hypothesis in half of the data, which is more powerful.
That's a great question. And I'm so glad I have all these co-authors here. In fact, it's something that I've wondered about, but I haven't at least gotten to think about it. So, in particular, a way of saying what you're saying is there's not a unique sufficient statistic in a given problem. And there is this notion of like minimal sufficient, but so you could reduce our data slightly with a sufficient statistic and GDT would work on that, or you could reduce it even more and GDT would work on that. So in this situation you're considering, the crudest reduction would be just to go to order statistics, because that's what sample splitting is. But you're asking, well, what if there were some simpler sufficient statistic? Would it be better to go all the way down to that? My intuition would say that it's better to go down all the way to the simplest sufficient statistic that you have available. But we haven't proved any result like that. Yeah.
When you're wondering an example regarding like the states when you like this correlated structure among them, say those variables of the state state, and then methods sort of address the situation like that, or they all
Right, so if the correlation structure is known, then generalized data thinning, we can do it with, we know how to do that. When it is unknown, that is something we're working on. Yeah. Yeah, so we used inference heavily to get to that point, right? But then at the end of the day, we had this thing that was over many random splits. So UW, I believe, hired Richard Guo to this department, right? And I believe his job talk was exactly on this question of when you I mean, he was focusing, I believe, on sample splitting or randomized procedures in general. And if you repeat something over and over again, wait, I believe that's what his talk was about.
Wait, so you're counting yet another question? That person?
Yeah, that's right. Yeah. I mean, it's a great question, but I think he and Rajan Shah have an interesting work on answering that sort of thing.
Any other questions? No, then Jake. Okay.
Nice.
Maybe one quick question. So it seems like you